Thank you. So yesterday I discussed mostly historical aspect of the Haldane gap problem. So I mentioned that although in many textbooks and so on, you can find the description that Haldane came up with his famous so-called Haldane conjecture based on the nonlinear sigma model with topological term. But in reality, that argument came later. So initially, he came to his famous conjecture based on the so-called Latin-Jarikis theory or Tomonaga-Latin-Jarikis theory. So this approach is now actually well known, I think, but I tried to review this approach, and in the spirit of the original Haldane's paper, which had been lost for a long time. So I will first review how we can describe various quantum many-body systems in one dimension using so-called bosonization technique or Tomonaga-Latin-Jarikis approach. I'm sure many of you are already expert, but let me quickly go through. So Tomonaga-Latin-Jarikis is a universal low-energy effective field theory. Which is nothing but free bosonic field in 1+1 dimension. Here, I mean, space is one dimensional and time is one dimensional. And so this simple field theory actually turns out to be effective field theory for many different kind of quantum many-body systems in one dimension. So this is also a special case of so-called conformal field theory in 1+1D. So there are various approaches to this. One well-known method is to start from fermions. But I want to discuss Haldane gap problem in the spirit of original paper by Haldane. So here, I'm not going to start from fermions, but take a different approach, which is, yeah. By universal, I mean, there are many different quantum body systems in one dimension, like a spin chain, like I discussed yesterday, and also electron system, like Hubbard model, or we can also consider many particle systems in continuum, like you can trap cold atoms in one-dimensional potential. Then these atoms can move freely in one dimension. And all those systems are very different at microscopic level. But if you are just interested in large scale or low energy property, then all those different systems can be described by the same field theory. By that I mean universal. So I want to derive this effective field theory, and there are various ways, but I want to take so-called phenomenological bosonization approach, because that was basically what was used by Haldane in his loss paper. So for this problem, so eventually I want to discuss spin chain, which is defined on the discrete lattice in one dimension. And this discrete nature of the lattice will become important later. But to start this discussion, I want to start from many particles moving freely, well, moving along one-dimensional space. So I start from one-dimensional space, and there are many particles which are moving and interacting with each other. And we can label the coordinates of each particle, like x1, x2, and so on. Then the Hamiltonian of such kind of system can be given by just kinetic energy of each particle and interaction between these particles. And I just assume two-body interaction. So my Hamiltonian would look like this. And of course, if there is no interaction, this is completely exactly solvable. But because of the interaction, this is a very non-trivial problem. So this is Hamiltonian in first quantized form. And if you use second quantization, then using the field operator, the Hamiltonian may be written like so using the creation annihilation operator, you can write down the Hamiltonian in using these field operators, and these two are equivalent. So we are interested in this kind of system, but of course, because of the interaction, in general, you cannot solve this problem. Although for delta function interaction case, and in case of bosons interacting with delta function potential, it's called Lieb-Lineker model, and actually it's exactly solvable. But as I also mentioned yesterday, exact solvability means that you can write down the exact ground state wave function, but it's not easy to read off physics from the exact solution wave function. So still, even for exactly solvable systems, this field theory approach is very useful, because once we know the effective field theory, you can compute many physical quantities of interest. Okay, so I want to derive some low energy effective field theory for this one. And by low energy effective field theory, I mean, I'm only interested in what happens in low energy limit or large distance limit, then even though we can start from this description with variables, dynamical variables showing the coordinate of each particles, but in the low energy limit, we are not really interested in motion of each particle. You cannot easily measure motion of each particle anyway. So we are more interested in collective motion of many particles. And the most typical collective excitations is density fluctuation. So you can create high density region and low density region. And if you leave the system alone, then this density variation will propagate. That's a sound wave. So we are interested in this kind of collective motion. Which is basically density variation. So instead of looking at the coordinate of each particle, I want to introduce a new variable which can describe this collective motion or density fluctuation. So to do this, here we are introducing the new field, which is sometimes called labyrinth field. And so this labyrinth field is function of coordinate x. And let's say monotonically increasing function, and we look at the intersection with 2 pi and 4 pi, 6 pi, and 2n pi. And once you assume this some functional shape of phi L, then this intersects with 2n pi. And this intersection represents the position of each particle. Maybe I should. Well, of course, in principle, you start from this configuration of many particles, and then you introduce this labyrinth field so that the intersection with this 2 pi n agrees with the location of particle. So in this way, the labyrinth field, once you introduce this field contains the information of position of every particle. So this. Other than that, monotonicity? Yeah, so I assume monotonicity. But there's no other, you can interpolate arbitrary. Right, yeah. So, yeah, of course, you can draw different curves as long as the intersection remains the same. But those small length fluctuation, we are not interested anyway. So eventually we are interested in large wavelength fluctuation of this field. So it doesn't matter much. So once you introduce this field. So the density of the particles can be represented by this labyrinth field, because, by definition, the density of the particle is given by sum of delta function located at the position of each particle. Then, using the property of delta function, the definition of the labyrinth field, this can be replaced by because the position of the particle is where this labyrinth field hits this 2 pi n. So you can replace this expression with this expression. And because of the nature of the delta function, you need to introduce this correcting factor. And then this delta function, okay, maybe. So this is only function of x, so we can maybe it's better to write this way. And then this kind of sum of delta function can be rewritten using the so-called Poisson summation formula. Which I think also high energy people, string people are familiar with. So this is already kind of remarkable because now density is expressed completely in terms of this labyrinth field, which is something like a macroscopic field. Then, so this is fine, but one problem is that actually this labyrinth field has to keep increasing because otherwise you cannot accommodate many particles. So usually we are interested in a situation where the density is constant in average, and then consider very large system or even infinite system in thermodynamic limit. So this labyrinth field itself has to keep increasing. And we are interested in fluctuation. So on average, this labyrinth field should increase like a straight line linearly. But then we are interested in sound wave-like excitation, which is fluctuation around this straight line. So we want to decompose this labyrinth field into average linear part and fluctuation part. So that can be done. So let's rho zero to be average density. Then this leveling field should, on average, increase like a 2 pi times rho 0x, because every time it crosses 2 pi n, you have one particle. Then the mismatch, the difference between this linear part and the actual leveling field represents a fluctuation. So I want to define a new field. So this is a new dynamical field, which represents density fluctuation. And here I put the factor of 2, which is actually not really necessary, but somehow the convention is that we introduce factor of 2 here. And here actually I'm following the very common textbook in condensed matter physics that is written by Yamagi. But there are many different conventions, and sometimes it's confusing. But because it seems like this textbook became a kind of standard in condensed matter physics using this convention. And actually, the discussion here for phenomenological bosonization, I'm largely following Yamaguchi's textbook. Although on the discussion of Haldane gap, I'm going to depart from this textbook and try to follow the original paper by Haldane later. So this is just a redefining, well, just rewriting the same thing using the new field phi, but still later it becomes important. So in terms of this new field phi, the rho x density can be given as, because if you take derivative, you first pick up this term, which gives you constant. So rho 0 minus pardon me? Oh, this times. So this is an expression of density of particles in terms of the new field phi. Now, of course, phi depends on space and time. So, yeah, so this is sum over all integer p, and as we will see later, somehow these terms with larger value of p are less important. So the terms with smaller values of p becomes more important. And in particular, if you take p equals 0, this is 1. So the leading term is just given by this. And another way of seeing it is that, as I said, this is the expression for density of particle at location x, but we are usually interested only in large-scale physics, and that's where effective field theory is useful. So usually we are not interested in density of particle at exact location x. So we are more interested in average of density over certain lengths. Then if you take, if you define average density over distance, which is much bigger than the average spacing between particles, which is inverse of density. Then if you consider such an average density, then you can take integral over certain lengths. Then most of these terms are oscillating because of this e to 2pix. So that's oscillating. So if you integrate, they vanish. So the only term which contribute to this average density is p equals 0. So if you do this, only p equals 0 term survives. And so the average density is given by rho 0 minus. So average density is just given by derivative of boson field. So this is one important result. But actually it turns out that to understand Haldane gap physics, actually this summation turns out to be important. That's point I will come back later. At first, I look at the average density, then it has very simple expression. So this is constant, and the deviation from the constant is just given by derivative of boson. Then so now we have this expression. Then I want to obtain the expression for the creation annihilation operator of the particle. And for that, actually, so far this discussion applies equally well for bosons or fermions, but for later convenience, here let me consider a system of bosons. For system of bosons. So here I want to consider the creation operator and annihilation operator. And if you take the product, so this should agree with the density operator. So which means that they are Hermitian conjugate. So from this, we can expect that psi of x is maybe written like square root of rho x and times some exponential of another field, theta. And this variable represents roughly the phase of the macroscopic wave function or something. And its Hermitian conjugate is like, well, in then so there are a lot of subtleties, but once we assume this kind of expression, we can determine the property of the new field theta. So theta is a field representing describing then what we need to have is we can consider the commutation relation between the density operator and this annihilation operator, for example. And then annihilation operator, by definition, annihilates particle at location x prime. So you need to decrease the number of particles by unity, just at x prime. So that means that if you first apply psi, then you have one less particle exactly at location x prime, which means that we must have this relation because of the definition of the annihilation operator. And this psi x consists of this square root of rho and this phase part. But this square root rho commutes with this density operator. So this implies the commutation relation of rho x and e to I theta x prime is minus. So this must be the commutation relation satisfied by these two operators, and here I'm interested at this moment this average quantity. So actually, as we will later see, the annihilation creation operator can have more complicated part, But this is what appears in the leading order once you consider average over certain lengths. So for that, yeah.
I thought that's almost, I mean, this is the definition.
Yeah. Yeah.
So what do you mean that it can have?
Well, yeah, good. Yeah, you're right. So maybe I'm confused. Maybe we can define this way. Okay. So maybe I should say the expression can be complicated because the rho x is okay. Yeah, that's probably correct statement. Yeah, thank you. Yeah, you're right. So, but okay. So at this point, let me focus on the average low bar for the moment. Then this average had a simple expression that rho zero, which is constant, minus 1 over pi times dx phi, as long as you consider average. So now this commutation relation, okay, so the constant always drops from commutation relation. So we can only focus on this part. So this expression means that the exponential of theta and derivative of phi obeys this kind of commutation relation. And to satisfy this, so, which means that 1 over pi and the commutation relation dx so this is a required commutation relation, and this is basically equivalent to so once you have this commutation relation between phi and theta, you can compute this commutation relation, and the result is this. So these are basically equivalent. So now we have introduced two fields, phi and theta. Phi came from leveling field, and the theta came from the phase of the wave function or something. And then they obey this commutation relation, and it still has derivative. So you can integrate, although there is some freedom of choice in integration constant. But if you pick one integration constant, so phi and theta obeys this commutation relation. So this is a signature of x minus x prime, means that if x is bigger than x prime, this is +1. And if x is less than x prime, this is -1. So it changes sign at when x equals to x prime. So if you take derivative, you recover this expression. So this means that this field phi and theta are subject to some kind of uncertainty relation because they don't commute. So you cannot simultaneously determine fix phi and theta at the same time. So if you fix phi, then theta is completely uncertain. And if you fix theta, then phi is completely uncertain. So actually, this is kind of generalization of the uncertainty relation is kind of natural because fixing phi means that you are fixing labyrinth field. So you are completely fixing the location of particles. Then they cannot have phase coherence. So the macroscopic phase of the quantum mechanical state becomes uncertain. On the other hand, if you fix theta, then that means that all the phases of the many particles are the same. So it's like a Bose-Einstein condensate, which doesn't really happen in 1D, but you can imagine a state with some fixed value of theta as a one-dimensional version of Bose-Einstein condensate. Then the phase takes us some fixed value. But in that case, the particles are condensed into the same quantum state. So you cannot really identify the position of the particles or density wave. So, so it's kind of uncertainty relation. So phi. So in condensed matter terminology, this phi describes so-called charge density wave fluctuation. Charge density. And theta describes phase of the quantum condensate. This commutation relation, the fact that they don't commute means that they obey certain kind of uncertainty relation. And also, I'm not sure if I can discuss with detail later, but it also turns out that these two fields are kind of dual to each other. So they are two variables describing the same thing, but in a different way. Yeah. Yeah, theta is compact, yes. Good question, very good question. So phi is in some sense compact, as long as you are only interested in physics inside the bulk. The reason is that the phi came from labyrinth field, as I introduced. So shifting phi by maybe pi, I forgot the exact number. Probably pi. Shifting phi by amount pi means that shifting the original labyrinth field phi L by 2 pi, which means that you shift each particle to the next one. So it's just like re-labeling the index of the particle. So you had x1, x2, x3, x4, and you can call particle number 1 as number 2, and the particle number 3, number 2 as number 3, and so on. Just by re-labeling the particles number, particle index, you can shift labeling field by 2 pi, and this field phi by pi. So it's like a shifting particle. So if you are only looking inside the bulk, you are just re-labeling, so nothing changes. So it's kind of symmetry. So in that sense, phi is effectively compact. But it's not truly compact as this field theta, which is truly compact, because, for example, if you look at the end of the chain, then delabeling the phi means that you are sending one particle outside the lead. So actually, if you look at the boundary or edge, the value of phi itself can have physical meaning. So if you include such end-of-chain physics, phi is not really compact. So it's a bit subtle, but in the description of bulk physics, phi could be regarded as a compactified field. Then if both are compact, it's also situation familiar to string theory people. And this phi and theta duality is T duality or something. Yeah. Okay. So now we have introduced two independent fields. So then the question is, what is a so now we got a fuse, and then question is, what is a Hamiltonian describing this system, effective Hamiltonian? And for that, we start from kinetic energy, which was given by so this was kinetic energy. But then we already have expression for this annihilation and creation operators. So we use this expression and plug in. Then in the leading order, what we have is this derivative of theta. So actually, of course, we are getting many more terms, but this turns out to be most important. Then, because if in the absence of any interaction, the ground state is kind of trivial, we are interested in interacting particle system. So the interaction part was given by something like this, rho x, v x minus y, y, dx dy. And here I'm interested in some short-range interaction, which doesn't have to be exactly delta function-like, but you can imagine for simplicity, this is something like delta function. But the important part is we consider short range. Then you can plug in here. And also, we had the expression that the rho x was rho 0 minus 1 over pi times dx phi. And there are higher order terms, but here let me focus on this term. Then if you plug in and do the integration, then apart from the constant part, the leading order is given by, again, the square of this term. So yeah, again, we have a lot of additional terms, but this, yeah.
So all these neglected terms are neglected in the order of what? In which parameter?
Yeah, good question. So I will later justify that all the additional terms are so-called irrelevant in renormalization group sense. So even if you get a bunch of other terms at the microscopic level, if you are interested in the low energy physics, so you repeat the renormalization group transformation, and in the low energy limit, basically all the terms disappeared. And then you end up with only this term, with maybe renormalized coupling, but that's basic story. Although sometimes some of the additional terms becomes relevant, then the low energy physics is no longer described by tonal attenuation theory or free boson. So that's when the situation becomes interesting. So, well, I'm going to explain in detail later, but the basic story is that when you can really forget about these additional terms, eventually, then the system is just described by free boson, which is critical with quasi-long range order power law correlation. But sometimes some of the additional term becomes relevant, which means that that becomes more and more important as you go to low energy physics. When that happens, basically the system acquires a gap, excitation gap, because additional terms becomes important. So in that case, you have a gap, like a Haldane gap for integer spin chain. So the real answer is it depends on the situation whether you can really forget. But first, let me sketch what happens if you can really forget about all those corrections.
There is one more question I have related to this. I'm calling from TIFA. Am I audible?
Yeah, I can hear you.
Yeah, so I'm interested to know, since we dropped the linear in phi terms also in this expansion, and it couples to the, it picks.
Yeah, I was cheating bit. So in general, you do get a linear term in dx phi. Yes, that's correct. And that corresponds to a chemical potential term. So, okay. So I forgot to add chemical potential. So chemical potential term is linear in dx phi. And that basically cancels the linear term arising from this interaction. Yeah, actually, the average density rho zero was defined such that there is no linear term in the effective Hamiltonian. So I skipped that part.
Thank you.
Thank you. Thank you for your comment. So, yeah, actually, the important question is whether we can forget these additional terms. That becomes important later. But first, let me suppose that additional terms you can forget. Then the effective Hamiltonian is just some constant times dx theta squared plus some other constant times dx phi squared. So now we have this simple Hamiltonian, but it still looks like involving two different fields. But actually, phi and theta are not independent degree of freedom because they have some funny commutation relation, but they are different representation of the same degree of freedom. So actually, you can recall the funny commutation relation that was so we had a funny commutation relation between the derivative of phi and theta. And this actually is identical to very standard commutation relation. That is, if we had the theory of free boson field, which is defined by Lagrangian density, like okay, so well, I can start from this one, but this commutation relation is also equivalent to you can apply this derivative to theta field as well. So this can be written as sign is wrong. Okay, maybe the sign might have been flipped, but anyway. So these two are equivalent. And let's suppose we have a free boson field theory that is defined by Lagrangian density. And then ask what happens if you quantize this free boson field theory. And then you can quantize using path integral formulation, which is also useful. But in order to compare with this commutation relation, we should do canonical quantization. Then the conjugate momentum to phi is defined by taking derivative of this Lagrangian by dt phi. Then what you get is 1 over pi times k dt. And okay, so this is a conjugate momentum. And once you have conjugate momentum, if you do the canonical quantization, so to do canonical quantization, you impose canonical commutation relation between the conjugate momentum and the field itself. So that is pi of phi at x and phi at x prime. So they must obey the canonical at equal time commutation relation. That is, this is like a P and Q in quantum mechanics. So this is minus I times delta. So this is a standard canonical quantization of free boson field. And now if you compare this expression and this expression, they are almost the same. Okay, so if you change the order and so on, then if you compare this expression with this expression, actually you can identify this conjugate momentum of phi with the derivative, x derivative of the phase field. Is equal to dx theta. Then this Hamiltonian can be written in terms of this conjugate momentum and boson field. So this effective Hamiltonian was integral of dx phi squared and the dx theta squared. But this dx theta can be identified with this pi of phi, conjugate momentum. So that means that effective Hamiltonian can be written completely in terms of phi field and its canonical conjugate. Trying to see the pattern. Where is the or maybe no. So you can rewrite this Hamiltonian. You can obtain as a low energy effective Hamiltonian for many particles in interacting in 1D in this form, assuming that you can forget about all those complicated additional corrections. And this Hamiltonian is identical to what you obtain from the canonical quantization of this free boson Lagrangian field. So this is identical Hamiltonian obtained. So you obtain the same Hamiltonian as you obtain from canonical quantization of free boson field theory. So in that sense, the low energy effective Hamiltonian of interacting many particles in 1D is free boson. So free boson field theory can describe long distance or low energy physics of interacting many particles, assuming that we can forget about all those complicated corrections, which I just assumed that we have to justify. So then, in order to really figure out whether we can forget about additional corrections, we first need to understand the properties or behavior of this free boson field theory. Or this is basically what is called Tomonaga-Rattinger-Leavitt or Rattinger-Leavitt. For that, we want to understand what the correlation functions of possible physical quantities in Tomonaga-Rattinger-Leavitt. And this actually basically what appears as a representation of various physical operators can be written in terms of fields phi or theta, and they are classified in various types. So typically, the physical operator can be represented by exponential of phi or theta, or equivalently cosine or sine of phi or theta, which are called vertex operators in string theory terminology. That is, which a type of exponential of 2i times p times phi, where p is integer. Actually, there are other types of operator as well, but this is most important class of operators. And you might ask why p is only integers, and that's related to your question that once we assume this phi is sort of compact variable that in the bulk that is invariant by delabeling the particles, then you can only allow this operator with, yeah. Mm-hmm.
Here there is a total derivative. That's a topological charge.
Yeah, yeah. Well, yeah, that's important, but I mean, in general, you can add linear term, like a dx phi, but that changes the average density of the particle in the ground state. So we de-define the field phi so that the average gradient dx phi in the ground state is 0. Yeah, that's by choice, yeah. So in other words, I had introduced this rho 0, which was the density of the particle, average density of particle in the ground state. That is determined by how much dx phi you initially had. But that changes rho 0, and rho 0 absorbs this effect, yeah. So, and actually, dx phi is still important operator in addition to this vertex operator. But the linear term don't appear in the Hamiltonian basically because we de-define the field phi so that you eliminate the linear term. But to be quick, I want to focus on this.
Physical radius of boson is something like square root k or something, I guess.
Okay, so well, in this representation, actually, the phi is compactified like
2 pi.
Pi or something. Yeah. Yeah. But that's because I chose this parameter in the front. That changes the critical exponent. So.
But in some sense.
Yeah. Right. Yeah. So in string theory, it's more common to fix this coefficient in the front. Then this compactation radius changes, but somehow in condensed matter literature, it's more standard to fix this, then absorb the effect in this parameter. So that's just a different convention. Yeah.
But just remind me that k was essentially coming from the coefficient of the delta function and.
Right, so it's determined by the ratio between the kinetic term and the interaction, yeah. So in this representation, I think the
strong coupling, strong interaction is large k.
Actually, I think in this convention opposite.
It's opposite.
Yeah, maybe it's maybe k, yeah. Sorry, I had to mention this. Yeah, thank you. So this k is roughly speaking determined by the ratio between the kinetic term and interaction term, and I skipped the details. But if you have very strong repulsion between bosons, k gets smaller, and if you go to zero interaction limit, k goes to infinity. Yeah, free fermion k equals 1. But it's not easy to read off from this argument, but it's known. Okay, then so to save time, I don't discuss how to compute the correlation function of these guys. So it's most conveniently calculated by going to path integral formulation and replace it with 1 plus 1D problem and do the integral, but I skip this part and I just state the result here. So if you compute this kind of correlation function, by the way, if you have different P and P prime, then the correlation function is 0 because of certain charge conservation. But you can have non-vanishing correlation function if you have same P with plus and minus. And this can be computed exactly for free boson field theory. And the result is determined by power law. And this exponent is given by 2 times k times p squared. So k, which appears in the front of this effective Hamiltonian, is important in determining the power or critical exponent of various physical operators. And for different type of physical operators, you have different value of p, and you have different exponent. So k is something called Luttinger parameter. In condensed matter literature, and this is equivalent to compactification radius in string theory literature. And this, as I said, basically determined by the strength of interaction, roughly speaking. So determined by strength. Yeah. Very good question. Yeah, that's what I wanted to discuss maybe later, but so yeah, so usual U1 symmetry in usual sense is well, the exact U1 symmetry of the system is the U1 symmetry of quantum mechanical phase. So that actually corresponds to constant shift of theta. Yeah, not phi. So in Lagrangian, okay, so written in this way, you cannot see theta. So it seems like this U1 symmetry is absent, but you can also rewrite the same Lagrangian using theta. So they are dual field. So in terms of theta, the Lagrangian is also like a d mu theta squared, but with coefficient replaced by k over 2 pi or something like that. So k appears in numerator instead of denominator. So then,
the topological charge is
yeah, actually kind of chiral charge. Yeah, so, well, yeah, you can say topological, yeah. And also, yeah, and you can also say that you can start from this Lagrangian, then because this theory is relativistic and massless or critical, so you can decompose this phi into right mover and left mover, and U1 symmetry, which is constant shift of theta, like a phase rotation, is equivalent to chiral transformation of phi. That is, you add some constant to right mover phi r and subtract the same constant from left mover phi r. So it's not apparent in this expression, but it exists. And then another point I want to make is that actually at the critical point, this massless theory actually has U1 cross U1 symmetry, because right mover and left mover, you can shift separately, at least at the Lagrangian level. That can be understood as a U1 vector times U1 axial or chiral. And the U1 vector corresponds to constant shift of theta. And there is another U1 axial, which is related to the translation symmetry on the lattice. Yeah. Or in the continuum space, yeah, it's really translation symmetry, maybe. Yeah.
But this also has an obvious constant shift symmetry. That corresponds to something strange.
You mean phi goes to phi? Yeah, that corresponds to translation symmetry. That's the point I want to make. Yeah. Okay, so yeah, if you are interested in this derivation, you can look up a textbook, and then okay, and this becomes important later, and because the time is limited, let me go to the argument by Haldane in his original paper, which had been long lost. I didn't find exactly the same discussion in any textbook, but it's still kind of illuminating. So,
So your exponent yesterday, eta, you would identify the 2k.
Well, actually, 1 over k or something, because yesterday I was discussing spin-spin correlation function, which corresponds to correlation function between exponential I theta and exponential minus I theta. So it's dual. So it has similar dependence, but the k is replaced by 1 over k or something. Yeah, exactly. Yeah. So that's important point, but somehow I skipped. Okay. So I want to explain what Haldane did in original paper. Actually, it's not easy to read paper, so it took some time to understand, but once you understand, it's very elegant. So he was interested in general spin chain, Heisenberg magnet with general spin. So I mentioned yesterday, so we can consider anti-fermagnetic Heisenberg chain, but with general spin quantum number S. And if spin quantum number is S, then that means that the eigenvalue of SZ can run from minus S, minus S plus 1, minus S plus 2, blah, 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 and S minus 1, and S. Yeah, of course, if you have spin 1/2, you have just minus 1/2 and plus 1/2, but this is a general situation. Then, yeah, I have been discussing many particles moving around one dimension, which looks different from Heisenberg chain. But you can always map this kind of spin system to quantum many particles on lattice by identifying. Yeah, there are various different ways, but one easy way is this lowest magnetization state with SZ equals minus S. You can identify with vacuum. And you increase this SZ by 1, then you interpret as there is one particle on the site, which is often called as magnon, but you can identify increasing SZ by 1 by presence of one particle, and minus S plus 2 identified with 2 particles. And these are naturally bosons. this is boson, which is called magnon. So in this way, you can map this spin S antiferrometric Heisenberg chain to some interacting bosons in one dimension. Then for this kind of system, I have explained how you can derive low energy effective theory, which is supposed to be free boson field theory, Tomonaga-Tinjariki. But as I mentioned, possible corrections can break down this description of Tomonaga-Tinjariki. So we have to be careful. And actually, Haldane did this carefully, and that was the point. So by bosonization, low energy field theory for the spin S Heisenberg antiferrometric chain looks like free boson or Tomonaga-Tinjariki. And let me first assume this picture. Then the density of particles, these magnons, we already had the expression in terms of phi field. That is repeating the same expression. Rho 0 minus 1/2 dxy times some summation over e to I 2 by p by x. Minus phi. So this is what you get as the expression of density of these bosons or magnons moving freely in one dimension. But then Haldane asked, okay, then what are the spin operators? Let's say SZ. So SZ, once you this identification is minus S plus number of bosons at each site. For example, SZ at site number J must be minus S plus number of bosons at the same site. Site J. But this spin chain was defined on a discrete lattice, like one-dimensional chain, J, J plus 1, J plus 2, J plus 3, and so on. And I explained this phenomenological bosonization, which applies to many particles moving on one-dimensional space continuously. So there is some difference. So the observation by Haldane in his original paper is that you must relate this lattice with a continuous space, or have an expression of particle number at each side in terms of this continuum expression. So that you can do by associating, so let's suppose this is continuous one-dimensional space, but actually you have only discrete lattice points. But you can divide this continuous space into cells like this. And then you can associate this cell to this side and this cell to this side and so on. Then the number of particles on this side corresponds to density of particles integrated over this cell. So that's what he did. So NJ is, okay, now I didn't introduce the lattice constant A, but let's suppose the lattice constant, that is distance between nearest neighbor, as A. Then Nj is given by j minus 1/2 times A to j plus 1/2 A. Then you have rho x. Then you integrate from the left end of the cell to right end of the cell. And it's a bit complicated, but you have this expression. So you plug in and do the integration. That's what he did. And then so it's a bit complicated, but you can do this calculation by partial integral and so on. And another important point is that here you had the average density of particle. So what is the average density of particle in this quantum spin chain? And the answer is that it's known from some rigorous theorem by Lieb and Mattis and so on, that when you don't add magnetic field, this model is symmetric about SZ and minus SZ. And ground state is unique and symmetric, which means that the total magnetization of the ground state of this spin chain, anti-fermionic chain, must be 0. That we knew from different argument. So the magnetization of ground state of this Heisenberg anti-fermionic chain must be 0, which means that the average of this particle number must be half of S. So that, and this, each side corresponds to cell of length A, which means that the average density of particle must be S over
Is 2s.
2S, yeah. Yeah, sorry, yeah, you're right, sorry. Yeah, you are right. Sorry, yeah. So the SZ average should be 0, so yeah, sorry, you are right. So this average must be S. Then this ground state average particle density must be S over A. So you must use this value here, and do the integral. Then, so if you do this, I will try to give more simple explanation maybe tomorrow, but here I'm following his original paper's argument. And he just did this integral using this expression. Then the result he obtained was this SZ operator at side J. You have somewhat different expression depending on spin is integer or half integer. So for integer spin, you have dx phi times 1 plus p natural number times some coefficient which we don't care as 2p phi of x. And this is for spin integer. But if you do the same integral for unit cell, for half integer spin, you obtain a somewhat different result. That is so you have different expression for even and odd p. When p is even, you have similar, basically the same result, cosine of 2p phi. But when p is odd, you have different result. That is -1 to j. Then you obtain sine of 2p phi. So the latter result is for spin half. So yeah, you have different result, and that's difference comes from this oscillating factor. So each term within this rho x is an oscillating function of x, like e to 2ip times pi rho 0x, but rho 0 is S over A. But if you integrate over the unit cell of length A, this factor gives a different behavior depending on whether S is even or odd. S is integer or half odd integer. Basically, if S is integer, then this phase factor becomes always 1 at the boundaries of the unit cell. So basically, you can ignore the phase factor. But for half odd integer spin, you have some different factor depending on the location of the unit cell. And then, so this SZ itself doesn't appear in the Hamiltonian, but the Hamiltonian had the interaction term like SZ. So if you consider the bosonized expression of SZJ plus 1, then you have always dx phi squared. But well, okay, so it's a bit complicated. But if you are familiar with field theory, if you consider this product, you should consider operator products expansion between this operator and the neighboring one. And yeah, basically dxy squared contains unity plus normal ordered dxy squared. And this has higher scaling dimension, but this is most important. And anyway, if you take a product of neighboring this operator, then because you have one, the leading term still comes from cosine of 2 phi. So maybe I should 1 plus cosine 2 pi phi. And you can also have cosine of 4p phi. Well, okay, sorry. It's related to this strange normalization of phi. We only have 2 phi times something, even or odd.
Summation of p or something, or there's no p?
Oh, sorry. Yeah, sorry. Thanks. Yeah, I didn't need p. I represented. Yeah, I kind of expanded this sum. Yeah, thanks. And so this is what you have for spin integer. And on the other hand, for half-odd integer spin, you have similar for dxy squared, but this can be decomposed into 1 plus something. And then now the situation is different because you have one, so the smallest exponent comes from p equals 1, but p equals 1 term, you need to pick up this p equals 1 term from this operator and 1 from the other operator or the other way around. And one of them have -1 factor here. So they cancel. So if you remember my PowerPoint slide presentation yesterday, I mentioned Berry phase cancellation of fundamental vortex, and that's actually exactly this factor. So because this odd integer terms coming from this operator and this operator basically cancels, at least the leading order, this sign term with p equals 1 cancel out and doesn't appear. So the leading term is 1 plus most leading term, non-vanishing one coming from this term, from this expansion is this cosine 2p with p equals to 2 term. So this latter comes from spin half. So we always have this kind of perturbation to Tomonaga-Tinja-Likit, but the question is, once we introduce this kind of perturbation, do they change the eventual behavior in the low energy limit or not? And that you can tell by renormalization group. So S3, J plus 1 introduces observations. To free boson field theory, that is nothing but tonality like it. And the question is,
I have a question here. Can I ask? Hello? Can I ask a question from TIFR? Yeah, so I have a question. What happened to the S plus S minus terms?
yeah, good question. So you can do the same, but eventually you only find the same type of operators. And maybe tomorrow I will explain why you only find those limited kind of terms. But I'm just showing maybe the simplest one in this line of argument, or what Haldane did in his original paper. But yes, you are right. We must analyze all the terms coming from S plus, S minus, and so on. But the final answer is that you can only find the same type of terms also from that terms. I'm just skipping that discussion. Yes.
Okay, okay. I was just worried about whether they are terms without gradients, but they are going to have gradients.
Well, okay, so yeah, you do get without gradient, but gradient is not essential here because I mentioned it's kind of technical, but you seem to always have dx phi squared always, but
okay.
This contains identity operator if you analyze carefully. So in the leading term, you can forget about this dx phi squared.
Ah, I see, I see. Okay, okay. That's fine then. Yeah.
So adding a mass term phi square, which breaks that shift symmetry.
Right, right.
That in the original speed chain is some anisotropy parameter?
No, it's related to your question. So phi square cannot appear in the bulk because it breaks the compactification. But if you have a boundary, you can break because shifting phi is like shifting all the particles to the right or left. So actually, interesting application, not in spin chain context, but you consider really electrons moving in one-dimensional wire or something. And you can apply the same field theory to modality like it. And then you can consider attaching this one-dimensional wire to some reservoir, like a quantum dot or something, or maybe some island or superconductor or something. Then this value of phi field at the boundary counts how many particles you provided to this reservoir or island. Then if you consider charging energy of the island, then you have additional term in the Hamiltonian like phi square over capacitance. And this phi is the boundary value of phi. Yeah, that happens. Yeah, but not, yeah. Right, no, yeah, it's basically forbidden by symmetry. Yeah, this symmetry analysis perhaps I will mention tomorrow, but let me quickly try to conclude. So if you analyze this SZ, then you get some perturbation to free boson field theory. But then the question to be asked is whether this perturbation becomes important in the low energy limit or not. And that you can analyze by generalization group. And renormalization group tells you that if you add some perturbation to critical point, fixed point, and if the operator at the critical point. Behaves like this is some operator at x and operator at 0. Generally behaves like 1 over F R times some 2x O. If this behaves in this way, then this x O can be regarded as a scaling dimension of the this operator. This operator at this particular critical point. And renormalization group tells you that this operator, if added to the Lagrangian or Hamiltonian, so we consider Lagrangian, which is given by critical Lagrangian, plus some small parameter times this O. Then this perturbation lambda O is relevant if this scaling dimension of this operator is smaller than the dimension of the space-time. And that's discussion I skip. You can find in some RG textbook. And in this case, I'm considering 1 plus 1D system, so 2-dimensional space-time. So this operator is relevant if the scaling dimension is less than 2. And if scaling dimension is more than 2, greater than 2, then this operator is irrelevant. So if you go to sufficiently low energy limit, you can ignore this perturbation if this operator is irrelevant. So the question is whether your perturbation has scaling dimension less than 2. And to determine this, we need to know this correlation function, but that we already have discussed. That is 2p squared k or something. So here we are concerned with 2yp phi x minus 2yp phi 0. And this you can compute and 1 over r to power of 2kp squared. So if you compare these two, then scaling dimension of e to 2yp phi is kp squared. And so the question is whether this is relevant or not. And it does depend on k. And if you consider XXZ type chain, as we discussed yesterday, k depends on anisotropy. Roughly because anisotropy, which is coefficient of SZ roughly gives you interaction. So the delta in the XXG chain plus SYJ, SYJ plus 1 plus delta SZ, J, SG, J plus 1. So you can generalize the Hamiltonian like this. Then if you change delta, then you can expect this k Rattinger parameter changes as a function of delta, which is generally complicated. For spin 1/2 case, 1/2 chain, as I mentioned yesterday, we know exact expression of k as a function of delta, thanks to the exact solution. But for general spin quantum number, we don't have exact solution, but we can suppose there is some function. And maybe I should keep.
I don't want to slow you down, but
yeah.
Why is it so difficult? The sign mapping that you just wrote down, if you translate that, don't you get relation between delta?
Yeah, good question. So, of course, at very naive level, you can have some expression, okay, by bosonizing the microscopic Hamiltonian. But you always have many corrections in the Hamiltonian like this. And what we need eventually is the Luttinger parameter describing the low energy limit. So that is parameter of the fixed point Lagrangian Hamiltonian. So this receives the effect of all the corrections. Even if the perturbations are irrelevant, those irrelevant perturbations eventually vanish in the low energy limit, but they do renormalize the parameters like this. So in order to know the precise value of Luttinger parameter, you need all the renormalization effect, which is non-trivial. So the best way to determine this parameter for actual spin model like this, except when there is exact solution that's very rare, is to do some numerical analysis. You can, for example, diagonalize a finite chain and obtain the spectrum and compare this spectrum with a finite size spectrum of conformal field theory. Then you can determine this Luttinger parameter. In general, it's non-trivial. But still, you can do very rough estimate by bosonizing the microscopic Hamiltonian. So if you just need some rough estimate, that might enough. But to determine precisely, you need all the renormalization effects. So usually in condensed matter, we determine this value numerically by comparing the spectrum. Okay, so so K depends on anisotropy. So in general, it depends on K, so we don't know what happens. But still, we can say something because so K is large for small or negative delta because, yeah, this negative delta represents attractive interaction somehow. And negative. And then increase delta means decrease. So that's can be roughly understood because K was defined like a Lagrangian in 1 over 2 pi K times d mu phi squared. So that means that if K is large, then this coefficient is small, which means that the phi can fluctuate a lot. So for very large K, phi is completely uncertain. But if you go to smaller K, then coefficient is large, means that this phi becomes almost constant. Well, at least up to some length scale. That means that this charge density wave order is solidified, which can be result of a strong repulsive interaction. So if you crank up delta, which is like a cranking up repulsive interaction between magnons, then you tend to drive the system towards a charge density wave, some density wave, fixed density wave. Then phi becomes more rigid. So that can be represented by decreasing value of K. So this you can expect intuitively. Then at delta equals 1, we need to have rotation symmetry, SO3 or SU2. We must have SO3 is basically equivalent to SU2 symmetry. And in general, this free boson field theory or Luttinger linkage doesn't have SU2, just U1. But at a special point, you can recover higher symmetry, that is SU2. And that happens exactly at the K equals 1 half. So as long as you are interested in the behavior of this Heisenberg chain that is isotropic with delta equals 1, you can only focus on the behavior of the system around k equals 1/2. So you can plug in k equals 1/2. So we are interested in Heisenberg anti-Heisenberg chain with delta x1. Then we can assume k is 1/2. Then the scaling dimension of e to 2i p phi is p square over 2. Okay. Then so let's take consider integer spin chain. Then from SZ-SZ interaction, we already have cosine of 2 phi, which corresponds to p cos 1. So S integer, we have p equals 1 perturbation, which gives a scaling dimension one-half, which is, of course, less than 2. So we have relevant operator. So even though we assume that the system is described by tonality theory, if you carefully analyze what kind of term you have, you basically have this term, which becomes relevant at least near the Heisenberg point. And this relevant operator drives the system away from the tonal generality. Then we expect opening of the gap. So this is relevant, opens gap in the spectrum, and also exponentially decaying correlation function. And this gap is nothing but the Haldane gap. And this is how Haldane first came to this conclusion. And this, but for half odd integer spin chain, the situation is a bit different because this p equals 1 term doesn't appear in the perturbation, at least as long as we look at this SZ-SZ interaction. So in principle, you also have to look at S plus, S minus, but as I said, the conclusion remains the same. Anyway, for half odd integer spin chain, we don't have cosine of 2 phi. You only have cosine of 4 phi, which corresponds to p equals to 2 in this formulation. So, oops. Half odd integer. Then we only have the minimum p is 2, and then scaling dimension is 2 square over 2 is 2. So this is exactly 2 at k equals 1/2. So this is called marginal operator. So it can be relevant or irrelevant, but at least for spin 1/2 standard Heisenberg chain, it happens to be so-called marginally irrelevant. So eventually it's irrelevant, but you cannot tell just from this analysis. But for standard spin chain, this perturbation happens to be marginally irrelevant. So can be marginally irrelevant. And this is actually the case for standard spin chain. So the system remains to be gapless critical. So this is a difference between integer spin chain and half-ordered integer spin chain according to Haldane's original paper. And, that's how he found it initially. And but still, it might look like a magic. And also, there was a question that what if we consider S plus, S minus, or if you add some other perturbations in the Hamiltonian. Actually, this difference can be understood in somewhat more systematic way, and that's perhaps I will discuss tomorrow. Yeah, sorry for going over time. Thanks.